Hello and welcome to the subject Advanced Strength of Material. And this is our third lecture. This is our third lecture. In the previous two lecture, we have discussed about strain energy. We have discussed about strain energy of we have discussed about strain energy of firstly strain energy of gradual loading. We have discussed next. We have discussed about the strain energy in sudden or impact loading. In this lecture we will see about strain energy due to due to self weight, and we will see some simple problems. So the lecture objective is to derive the expression of strain energy due to of a bar due to self weight. Though this expression, this derivation is not so important, but you should understand this derivation, because by understanding this derivation you can understand the terms used in the equation, so that you can make the you can make the derivation make the problem very easy. So in your syllabus, what is there? The strain energy expression under the strain energy expression due to self weight is in your syllabus. So now we will see about we will see that our and at the end of this lecture we will see some numerical problems. So let us consider one bar, that is uniform cross section bar, shown in here. That uniform cross section, in this uniform cross section bar we have to calculate what? We have to calculate the strain energy. So for calculating the strain energy, there is, in this case, there is no external load. That means there is no load is applied here, but there will be a strain energy, or there will be a energy stored due to self weight of the body. To understand that, to derive the expression of that strain energy due to that self weight, we have to first do what? We have to first make this we have to first consider a small element. We have to first consider a small element dx. Now weight on the length of on the bar of length x, weight of the bar of length x, that this weight acted upon the upon this portion, upon this small portion. So this weight wx is the weight of the bar of length x, that can be given by volume of the bar of the length. And here we know that, here we assume that L is the weight per unit volume of the material. So Wx, or weight of the element, weight of the bar of x length, that weight is equal to volume of the bar of x length, that is the volume of the bar of x length, and weight per unit volume. Now now we know the volume can be written as area into length, that is A into x, and rho is the mass per unit volume. So we multiply that, so that would give us wx is equal to rho ax. Wx is equal to rho ax. This means this rho ax is the weight of the bar of length x. Now this weight, where this weight is acting? This weight is acting on the element dx. So by when it is acting on the element dx, what happening? The element dx is deforming. Element dx is elongated. It is elongated by which? What? It is elongated by a small strain, or a small elongation is there. If we denote that elongation with del d del, this is the elongation. Now so we can write the strain. We know the expression for strain. The expression for strain in dx will be elongation by its original length, that is del d del by dx. This is the strain. Now as per we consider stress. Stress is the force per unit area. So what force acting to deform the element dx? The force is the weight force, the weight of the bar of length x. Now this weight is acting inside the acting in the dx. So in the dx, what is generated? In the dx, reaction is generated. That reaction is obviously equal to the weight of the section xx. So now weight of the section x, stress can be written as weight of the section xx by area of the section. So this is the weight of the section by area of the section. So weight of the section is our rho ax and area of the section is a. So that give us stress is equal to rho into x. See, stress is equal to rho into x. See here, stress is equal to rho into x. So now we know up to elastic limit we can follow one rule, that is Hooke's law. Now Hooke's law can be given as we all know, that is Hooke's law can be written as stress by strain. Now E is equal to stress by strain. Now we calculate the stress is equal to rho into x and strain is equal to d del by dx. Now if we simplify, that means we put this value here and then we got what? We got rho x dx by d del. Now from here we can write extension or elongation can be written as del d del is equal to rho by e x dx, rho by e x dx. Now this is our deformation. Now for strain energy calculation, we know strain energy is equal to energy stored. So that means strain energy of that element, of that small element, the u is given by half into wx. Why half into wx? Because only the average weight will be acting on the body. So that is half into wx and d into del, d into multiplied by d into del. Now putting the value of wx and d into del, what we got? We got du is equal to half rho square a x square dx by e. Among them, understand this, among these terms, what happened? Among these terms, rho area, this area and this x, rho area and this e, rho, that means mass per unit volume, a, that means cross sectional area, and e, that means Young's modulus. All of these terms are constant. Only this x is not constant. So that's why what we do, we will multiply. While we do integration, we will put this constant value outside of the integration. So now this du is the only du is the what is du is the strain energy of the small element. Now to calculate the strain energy for the whole element, we have to integrate it from 0 to L, because the length is, or the x is varies from 0 to L. So that's why the u will be is equal to 0 to L half rho square a x square dx by e. Now that would give us what that would give us this value, that is u is equal to half rho square a by e integration 0 to L x square dx. Now integration of x square is given by x cube by 3. This is the integration of x square. So if we put this value here, along with 0 to L upper and lower limit, that would give us u is equal to 1 by 6 rho square a L cube by E. Remember this value, only remember this value for your question or for in your syllabus. Just this value, this expression is there, and this expression is important. So this expression, from this expression, how the question will be asked, you will be given the value of strain energy. Now you have to calculate, and you will be given all the other necessary value. Then you have to calculate the length of the workpiece, or you have to calculate the stress generated in the workpiece. So that calculation will be very easy, and you will practice more problem on strain energy from any source. And if you have any problem, you may ask me. Now we will see some problem. So first we will see a new problem that is based on the sudden loading. So that is this. So say, see a steel rod which is 2 mm long, 2 meter long and 50 mm in diameter. The axial pull of 100 kilonewton is suddenly applied to the rod. Calculate the instantaneous stresses included, and also in the instantaneous elongation produced in the rod. And the value of Young modulus is, or value of modulus of elasticity, is given. Now as per the question, what is given, it is given that the length will be 2 meter, that gives us 2 into 10 to the power 3 mm, and the diameter of the bar is 50 mm, that gives us the area will be 625 pi. Now as the load is suddenly applied, to total value of the load is suddenly applied, and that value is equal to 100 kilonewton. That means 100 into 10 to the 3 newton. Now G is given. So that would, now the stress will be 2p by a. Why 2p by a? Because in case of sudden loading, the stress intensity will be 2p by a. So that would give us 101.86 Newton per millimeter square, and elongation will be del L by E, that is the 1.0186 mm. So these are the values of strain energy, of stresses and elongation. And this problem is, this type of simple problem you will see in the semester. Now in the second problem, this problem I have given as assignment. So now I will discuss this problem. See what is given here. Also the tensile load of 100 kilonewton is given, but it is gradually applied. So as that here it is said that the load is gradually applied. So we use stress intensity formula as P by A. Now if here also try this problem, you will try this problem by taking 100 kilonewton load along with by taking 100 kilonewton load as sudden loading. So if you take it sudden by sudden loading, what will happen? The the load will be the the stress will be 2p by a. So and the value will be according to that. So this is the simple problem, second simple problem. And thirdly, this problem is also discussed earlier. The value of strain energy will come from this equation. Now another problem, for another discussion of another problem, if there is value of a if there is all the values, that means area, cross section area, length, and uh, weight per unit volume is given for a body, then the strain energy due to self weight, that problem will be for that problem will be, first we have to calculate all those values, and we have to put that value at the formula, that is u is equal to 1 by 6 rho square a l cube by e. So we will use that formula, means we will use this formula, we will use this formula to calculate the cell deformation, or to calculate the energy stored due to cell weight. So these are the problems. So I hope you will have a great good insight on the topic strain energy. This is the last lecture of strain energy topic. In the next lecture we will see about the we will see about in the next lecture we will see about next our next topic. And till then, if you have any problem, just feel free and ask me. So thank you for being here.